Look at a chessboard. How many squares of different sizes can you find along the grid of a chessboard? 8x8 chessboard. There are many different squares, right? Yeah. Look at that. So here, this is a square, right? Okay. How about this one? Another square, okay? Then another square, many different squares. Here we need to do the counting. Count all possible squares you can find in this chessboard, okay? Along the grid, right? Yeah. So think about, yeah, what method or what property, you need to use here, okay? Yeah. Yeah. Think about different sizes, how to handle the squares of different sizes. A what? Yeah. So yeah. Diagonal. Do you want di diangle? Yeah. What? Going have sizes one by one. Yeah. Good. Yeah. So Madison. Yeah. Your observation is correct. Smallest size 1 by 1. The largest size 8 by 8. That's a good progress. That's good progress. All right. Diagonal. All right. Yeah. So right. So here you view using the diagonal way to view. Yeah. All right. Yeah. Because for each question, we may have different views. All right. Different views. Yeah. Some of the views could result easier solutions, and some of the views could result in harder solutions. Yeah. All right. Yes. Okay. Yeah. All right. Yeah. So let's do the thinking, try to solve it using Madison's suggestion. All right. Madison's suggestion. All right. Yeah. If you start a corner. Oh yeah, corner. Then progress across it will, yeah, right. Yeah. Corner. But if you use that way, try to cover all the possible squares. All right. Don't just count the diagonal squares. Yeah. So Dakota, so when you use your diagonal way, do not miss some of the squares. All right. Yeah. Yes, that's the reason. That's because when I see your diagonal, this word, I realize you may miss some of the non-diagonal squares. Yeah. So that view, that means this view is not the best view. Okay, the diagonal view is not the best view. Horizontal view, vertical view, better, because you can cover all the possible squares. All right, yeah. But here I like to follow the suggestion by Madison's suggestion. Yeah, so let's do it, because there are different sizes. Yeah. And 1 by 1 through 8 by 8. Okay, yeah. And when we start, here I like to convey one commonly used thinking way. Yeah. 8 by 8, that's the easiest size to be counted. Easiest size. All right, yeah, so let's count. All right, case 1, let's count 8 by 8 squares. How many? So that number, Madison already put there. 1, right? Yeah, so that's 1. Yeah. Subtotal, yeah, we can, subtotal 1. Yeah, here I just the number 1. All right, then 7 by 7. How many? Okay, yeah, let me look at Madison's input. Overlapping, yeah, overlapping allowed, yeah, allowed. So the only thing we need, we care about, it's a square. Okay, yeah, it's a square. Yeah, so overlapping squares, that's fine. Yeah, no problem. All right, 7 by 7, 4. Yeah, all right, so here 7 by 7. Yeah, because 8 by 8, that's easy. 7 by 7, look at the horizontal. How many 7 by 7 we can have? Horizontal. All right, 7, this is 1, 7 by 7 square. Then another one, 7 by 7. So horizontally, you have 2, right? Yeah. Horizontal, yeah. So this direction, horizontal. Vertical, you have 1, you have 2, right? Yeah. You have 1 vertical here, you have 2 vertical here. Okay. So horizontal, you have 2 different cases. Vertical, you have 2 different cases. So now 2 by 2. The total number 2 by 2. So that's how the number 4 comes from. All right? Yeah, comes from. So that's 4. All right. Then next one, you notice some rule, right? 6 by 6. Number of squares in the size 6 by 6 sizes. Horizontal 3, right? Vertical 3, 3 by 3, 3 square. Okay, yeah. Now you can do the analogy for all the possible sizes. 5 by 5, number 4 by 4, right? Because you look at horizontal possibilities, vertical possibilities, then 2 dimensions, multiplication. Okay, multiplication. Yeah. All right. Next case, 4 by 5, size. Yeah. Here, this column, the first column, sizes, size. Okay, or size. All right. This column, the number. Okay. Yeah. 5 by 5. All right. 3 by 3 size, and the number 6 by 6, 6 square. Okay, yeah. 2 by 2, 7 by 7. In the last case, 1 by 1 size, the number 8 by 8. How about that? Okay, all right. Yes, yeah, Madison noticed the inverse. Good, yes, yeah, right, inverse. All right, yeah, so that rule. So you need to observe some special rule here. All right, yeah. So now the total answer, yeah, so you can calculate the answer 1 square plus 2 square plus 3 square, dot, dot, dot. So the last one, 8 square. Okay, yeah. So then you can find that number. Here, I do not do that. Yeah. So I allow you use calculator. Okay, I allow you use calculator. Okay, yeah. So we can get the answer. Yeah. Now the summary. Now the summary. Calculators on, yeah, allowed. Calculators allowed on the exam. Yeah. And yeah, also allowed. So regular calculators and online calculator, even online calculators are allowed. I hope you know some online calculators, because the calculators, regular calculators on your cell phones, those may not be very powerful. Think about some of the operations. I'm afraid you cannot do, like a log, square root, roots, sine, cosine, yeah. But online calculators, so you can find some powerful online calculators, yeah. All allowed, okay? Yeah, all right. Here, I like to do the summary, yeah, after this question, so after you see the solution here, I want to convey one point here. So we are given data. So the chessboard, the number of squares on the chessboard, that's the data we have. And we need to process the given data to find some answer. All right? So here, in the real world, we are given initial data. Okay? We are given initial data, all different kinds of initial data. And then we need to do data processing. Based on the requirements, we need to do certain data processing. Okay? Yeah. So when we do data processing, there is one special consideration here. You can see in this example, that is organize the given data. Organize the given data. Yeah. The original data may not be organized. It's quite randomly given, the original data. Okay? Yeah. But sometimes you need to do some processing to make your data organized. So in this example, we can see we organize our data in different sizes. Okay? In different sizes. At the beginning, we do not view the given data in different sizes, right? Yes. So that's the reason, when, let me see, Madison, right? When Madison gave us his suggestion, actually, he recommends some special way to organize the data by sizes. Organize the data by sizes. That's an important observation. Very important observation. So then we follow that direction. We organize our data in different sizes. The reason here we can enjoy the benefit of that data organization step, because for each size, the counting is much easier. Okay? For each individual size, the counting is much easier. Okay, so we can do it quickly. Yeah. Then we put them together, we add it up, so all the sizes, very easy. But you need to make that step first. You need to make that step first. Data organization step first. All right? Yeah. So here you can see, although these two examples are quite special, but there are some common principles, common ways that we use in general problem solving. Data organization, that's a common approach that we need to use in our real world computing problem solving. Okay, and the first one, discover some special properties. Probably most of the time we need to discover some special properties. Yeah, the question is how to discover, right? That's another question. How to discover special properties. Now, so later when we have more examples, I will give you some suggestions how to discover different properties. Okay, all right, yeah. So we complete our topic 8.1. Yeah, just these two examples. Yeah, yeah. Total 204. I do not know by myself. I need to, do it on paper. Yeah, yeah. So then, oh, there is, yeah, actually, when we do it on paper, we get some number. But how do you know your answer is correct or not, right? When you do the calculation, you try your best. But the question is, how do you know your answer is correct? Think about that, right? Yeah. And in order to answer the question, make sure your answer is really correct. Although you can do the calculation a few times, but another better way is try to calculate the same formula in different ways. Yeah. Can you find an example that is 1 square plus 2 square plus n square? Yeah. Because there is a formula calculate 1 square plus 2 square dot 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 plus n square formula, right? Yeah. Because when you learn the discrete math, there is this formula, right? Yeah. As I remember, 1/6 times n plus 1 times 2n plus 1. Something like that. Yeah. If this formula is correct, let's plug in 1/6. So here our n is 8, right? 8 times 9 times 17, right? Yeah. So 3, 4, right? Yeah. 17, 51, 4. Good. Yeah. 204. Good. The same as the one Dakota give us. Yeah. But here I calculate in different way. Yeah. Okay. I calculate different. There, when we calculate the same formula in different ways and they have the same result, then we have more confidence, right? It should be correct. Yeah. Yeah, because two different ways, it's very hard. You do it wrong in two different ways, but you get two same wrong number. How about that? Yeah. What is that formula called? All right. Yeah, good. Yeah. I need a little more space. Yeah. All right. Because this slide, I use up all the space. Yeah. Let me borrow the space here. Yeah. The formula. All right. Yeah. Okay. Yeah. Since you asked me the formula, yeah. Well, I still keep this one. Yeah. Because later I will post this notes. You can download my, annotated notes later. Yeah. The formula. Yeah. For Dakota, for your question, I like to start from the first formula that everybody knows. All right, that's a simple formula. That's 1 plus 2 plus 3, the consecutive numbers through n. I believe all of you know this formula. No, this, yeah. That's 1/2 n times n plus 1, right? Yeah. All right. Then I believe in your discrete math, yeah, the prerequisite for this course, discrete math 3000. Yeah, if you still keep that textbook or, you can, all your notes, you can go back and check it. Yeah. The formula should be, yeah, we need to find this for, we need this formula, okay? N squared. Then, yeah, it's much more complicated. To find this formula, it's much more complicated. Yeah, but the answer is 1/6 times n plus 1. But the last factor is 2n plus 1. 2n plus 1. So this is the formula. Okay? Yeah? So, yeah. Yeah. So here, I believe it's correct. So that's why I plug in the numbers, we got the same answer. So I feel it is correct. Okay. All right. If this had been a coding project, would we have gotten full credit had we do either way? Yes. Yeah. Coding project, yeah, either way, yeah, if it's correct, if your answer is correct, okay, yeah, because a coding project, you will run a for loop, right, to do the calculation. Yeah, that's fine. So for the coding project, I assume you have two different ways to do the calc. The first way, just to write a for loop, so add up the sum of all these consecutive squares. Another one using this formula, 1/6 times n times, plug in to find the answer, both correct. Okay, both correct. And actually the first way, so actually the formula way is much faster. The formula way is much faster than your for loop way. So when you do the coding way, there is a for loop way. For loop way and the formula way. And the formula way is much faster than the for loop way. Yeah. Okay. Yeah. So that's why if it's possible, we always try to discover some formula. But sometimes the formula may not be available, so we have to take the loop way. Okay. If the formula is available, we always pick the formula way because we can find the answer much faster. Okay. Later, we will have another problem with the similar situation. That's the Fibonacci numbers. Fibonacci numbers, you can calculate the Fibonacci numbers using the for loop way. But there is a formula for the Fibonacci numbers. So you can also calculate Fibonacci numbers using the formula way. How about that? Okay, yeah. But that's a later topic, our module 3 topic. Okay. All right, yeah. So already 7:30, so I need to move to the next topic. All right. Oh, I know, yeah, before I move to next topic, I noticed there is another question. Some student asked another question. I didn't give the response. So let me, yeah, I missed that. But I suddenly, I noticed that. Oh, yeah, let me check it. Okay, yeah. Yeah, I saw this, right. Yeah, I saw this from Jeanette. Yeah, from Jeanette. Would the pattern hold true for 3D or ND? Good. That's a really good question. The answer is yes. The pattern hold for even, yeah, not just 3D, ND dimensions. Yeah, that's a really, deeper question. Yeah, I like it. I like it. N dimension. Even you can push it to the n-dimensional case. Yeah, because not many people can imagine n-dimensional case, right? How many of you can imagine n-dimensional case? Right? It's hard, right? Yeah, but Jeanette. So yeah, from her response. Yeah. I'm not. Yeah, I guess. Yeah. If I'm wrong, just correct me. Yeah, Jeanette. Yeah.
I do work beyond two-dimensional space. That's why I was asking.
Right. Great. Because this question very deep. Yeah, very deep. Yeah.
Is there a formula for n dimensions?
Just the product of, product of all the numbers for, all the dimensions. Yeah. Straightforward multiplication.
Thank you.
Yeah. Right. Good. All right. Yes. All right. Yeah. Let's move on. Yeah. Yes. For most of you, if you can imagine 3D, that's already super. Yeah. 3D. It's hard to imagine. Yeah. But sometimes we need to consider n-dimensional. Yeah. Here, yeah, let me just say a few more words, because you mentioned that. I like to, talk about n-dimensional case. Because many of you may feel why we need to consider high dimensional case if the dimension number is higher than 3, right? Because in our real world, can you imagine anything has dimension higher than 3? Right? Yeah, it's hard, right? Yeah, good. Yes, you have a lot of background. Yeah. All right. Yeah. So, yeah. But actually, we may encounter many data processing with much higher dimension. Yeah, not just 2 or 3. It could be 100, 1,000, very high dimensional data processing. That's possible. Yeah. The situation is just like this. Yeah. Because when we do scientific experiments, in order to make some very complicated scientific experiments, there are many control factors, right? Yeah, because you need to adjust, temperature, many different things, many different factors you need to consider. Each factor, we use one dimension to represent it. If you have 100 factors, you need to use 100 dimensions. In that way, you need to handle multi or high dimensional data. Yeah, high dimensional data. Okay, yeah. So even if you cannot visualize, yeah, it's because it's hard to visualize 100 dimensional data, right? How can you visualize in your mind? How can you visualize? Nobody can visualize it. Yeah, but we just treat it as formula. Yeah. Treat it as formula, 100 different dimensions. Can we use a formula to represent 100 dimensional data? Yes, we can. We can. Yeah. So here, for example, x1, the first dimension, x2, second dimensional, and so on. x100, that's this is a 100 dimensional representation as a vector, as a 100 dimensional vector. Yeah, we can represent it. All right. Yeah. Anyway, yeah, let me just stop here. Yeah. So let's continue our next topic.